So let's look at some examples now. So let's say we wanted to do this integration. So integrate 3x to the fourth minus 5x squared plus x dx. All right, so what we're going to say is we have a 3 as a multiplicative constant that can stay there. Then I want to integrate x to the fourth. Well, how do we do that? We take x, we're going to add 1 to the exponent and divide by the new exponent. So adding 1 is 5 and divide by that new exponent, 5. All right, minus, keep the 5. Now I have integrating x squared. X, add 1 to the exponent, giving me 3, and divide by that. All right, plus, okay, now I have integrating x. Well, that's x to the 1, so I'm going to add to the 1, giving me 2, and divide by it. So x squared over 2, and then I have to remember a plus c. So there we go. All right, so now here's the key. I want to integrate x cubed plus 3 over x squared. I am not allowed to just integrate the top and integrate the bottom separately. No, 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 no. Just like you couldn't do it with differentiation, you can't do it with integration. But what I can do here is I can put it in a better form. So I'm going to work with this. I'm going to split it up and do x cubed over x squared plus 3 over x squared. So I'm going to do a bunch of algebraic manipulation before I get to any integrating. So x cubed over x squared is just x. And then, just like with differentiation, I'm going to take this term here and rewrite it as 3x to the minus 2. All right, and then that's the thing. So now I have it in a better form, and I actually can carry out my integration. So integrate x, we saw that before, x squared over 2 plus, now integrate x, so there's a 3 there that's being multiplied, and then I need to integrate x to the minus 2. Well, that would be x, so now add 1 to the exponent, giving me minus 1, and divide by that new exponent. So over minus 1, and then I still need a plus c. So I could write this as x squared over 2 minus 3x to the minus 1 plus c, or somebody might want to see it as, something like a half x squared minus 3 over x plus c is just another way of writing it. Not necessarily better right now, but just another way. All right. That's somewhat similar to what we have here. Again, I want to do some manipulation algebraically before. I want to do x over the square root of x plus 1 over the square root of x, because I can break this up. Whoops, don't forget your dx there. All right, x over the square root of x is just the square root of x, or I'm going to convert it and write it as x to the 1/2, plus 1 over the square root of x is actually x to the minus 1/2. So I've got it in a very good form. In other words, I have it in just powers of x. Anytime I can get it into just powers of x, that looks good to me. Because now I can just do the power rule. So I have x, I'm going to add 1 to this power. So 1/2 plus 1 is 1/2 plus 2/2. That's 3/2. And now I'm going to divide by 3/2. But instead of dividing by 3/2, it's easier just to multiply by 2/3. And you see how that 2/3 would cancel the 3/2 coming down on a derivative. All right, plus, all right, x to the minus 1/2. Again, add 1 to the minus 1/2, giving me positive 1/2, and divide by 1/2, but that's the same thing as multiplying by 2. All right. So then we get another plus c, because we always have to have that plus c. And there we have it. So again, you might see somebody write it as 2/3 x to the 3/2 plus 2 radical x plus c, but that's the same thing. Okay. Integrate cosine over sine squared x. Well, again, if it doesn't look to me like anything that I recognize as the derivative of something, then there's more to be done. So with something like this, I'd have to play around with it. I'd have to say, okay, well, maybe I just don't see it. So what if I split the sine squared down there? So instead, I did cosine x over sine x times sine x. So that's what sine squared x is. And then I wrote it as, say, 1 over sine x times cosine x over sine x. All right. It's still not, I don't see it yet, but if I keep doing it, what is 1 over sine of x? Well, that's cosecant x. And what is cosine x over sine x? That's cotan x. Whoops, put that x a little closer. dx. All right, so now I look. And is this something that I recognize as a derivative? You know, with constants or negative signs possibly added. Yes. Cosecant cotan is the derivative, basically the derivative of cosecant x, but it lacks the minus, so I need the minus there, and I get plus c. So what we notice is that I was able to do this problem even though I didn't immediately see what this was, but by playing around and putting it in a particular form, I was able to solve it. Now, that doesn't mean that if I start changing a few things in here, if I put over sine cubed, or if I put cosine squared there, that it'll be as easy. It had to do particularly with the form of this, and so not every integral is going to be easy to do. In fact, we're going to see that there are plenty of integrals for which there is no method to get the answer. They can still be integrated, but it has to be done in a different manner. And this idea won't work. Okay, so how about integrate x squared plus 1 all squared? Again, I can't do anything, so I can't really do yet any sort of chain rule. There will be kind of a reversal of the chain rule, but the only way I'm going to be able to accomplish this right now is to actually multiply this out first. So we'd be integrating x to the 4th plus 2x squared plus 1 dx. And I know that if I have something like that, have just a polynomial, that should be fairly easy to integrate. Because I just do x to the 4th gives me x to the 5th over 5 plus 2. X squared gives me x to the 3rd over 3. And x gives me just x. And then add a plus c. And again, some people might like to write it instead as 1/5 x to the 5th plus 2/3 x to the 3rd plus x plus c. Both are fine, depends on what you like to look at.